Good afternoon and welcome to the Embedded Executive Podcast. My name is Rich Nass. I am the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for embedded computing design. My guest this week is David Doyle, the President and Managing Director of Heidenhain. How you doing, David?
I'm doing great, Rich. Thanks very much for having me today.
My pleasure. I have a feeling that our audience is not familiar with Heidenhain. So just real quick, who are you guys?
So very interesting company, I would say. We're leaders in advanced motion control technology, and we serve three main, I would say, vertical markets. We're best known in the machine tool space, but the fastest growing business for us is in the electronics capital equipment market, serving the semiconductor front end and back end applications. And then we have a very strong portfolio of products that serves the general automation and robotics market. There's a whole host of, let's say, entities within the Heidenhain group that have niche, let's say, or specific technology that serves specific use cases, and then address smaller subsegments, including industrial, medical, life science, and renewable energy markets as well. So a very diverse company. We're headquartered in Traunreich, Germany, Bavaria. We have a global footprint, serving all of our OEM partners around the world.
Okay, let's get on to the subject at hand here. We want to talk about the role of precision metrology and motion control for semiconductor manufacturing. Explain that to me, because those are bigger words than I normally use. What does that mean? Precision metrology.
Yeah, so in a semiconductor manufacturing operation, there's let's say a series of process layer execution steps, right? From patterning to etching to material deposition. In each of those subsequent steps, there's metrology validation of that process in a statistical process control context. So for that, you need to have capable metrology systems that either measure the material composite or material properties, or perhaps you're looking at structured elements of the semiconductor device, whether it be a critical dimension or an overlay measurement or registration of layer-to-layer performance. So precision metrology requires, let's say, positioning the wafer under a stir, whether it be optical or otherwise, where you're gathering data, and that data needs to have, let's say, a level of repeatability and precision such that you can measure the critical parameters within the process. Heidenhain's role in that is to deliver, let's say, motion control solutions that either position the wafer or position the sensor, such that you're measuring reliably in the right target area on the wafer, whether it's a test site or whether it's on the product itself. So the importance of that is, how do you maximize the throughput, precision, accuracy of the metrology that you're applying to the process? And Heidenhain provides encoder technology for subsystems that are used in that context, or we provide full wafer stage technology so that the wafer can be handled appropriately in either a metrology platform or maybe even in a process tool as well, where there may be integrated metrology and integrated into the process tool.
Is this technology specific to semiconductor manufacturing, or is this something that applies to other areas as well?
Well, I would say the high-end, let's say, capability that we provide from an encoder technology is typically targeted at advanced applications for lithography and metrology in the semiconductor context. There are other, let's say, product portfolio elements that can be applied into automation or machine tool, and they have perhaps different criteria associated with the motion control objectives. So in robotics, it may be high precision, moving towards high accuracy these days. For the new use cases of robotics in surgical applications or in cobot applications, where you have to have safety and reliability topics addressed. In Mitul, our niche is in 5-axis control, where we're basically machining metal parts that are highly complex, that require 5-axis dynamic control to form the part and to have surface finish that is necessary for that application. In some cases, it could be mold and die, where you're manufacturing high volume parts using a mold that's manufactured through a machining process. And in that case, the algorithms that we use to manage the control of a system doing those advanced cutting steps and finishing steps requires advanced technology as well. So, semiconductors is definitely a challenging space in terms of accuracy and precision, particularly in lithography and metrology and in spin. But there's also advanced applications in other markets as well that serve.
When you talk about accuracy and precision, would you quantify what you're talking about?
Yeah. So let's say you want to measure a test structure in a scribe lane on a semiconductor wafer, and you want to measure a multi-stack of films, and you want to look at thickness and refractive index of those materials. Mm-hmm. You want to locate the measurement spot, the object of interest, below the optics, whether it be normal incidence or, let's say, oblique incidence of light relative to a sensor. So the types of accuracies precision that we're looking for is, essentially trying to get down less than a micron of spot placement accuracy in the scribe lane, and then in the, let's say tens of nanometers in terms of precision of placement, so you can reliably place that spot where you want it to. In the lithography case, it's a little bit more complicated in the sense that there is a requirement to control, let's say, a reticle stage and a wafer stage. So when you're printing structures in resist and you're exposing that resist, you're interested in aligning to the, let's say, alignment targets that are used layer to layer, such that you have optimal resolution, or sorry, optimal registration from layer to layer. So overlay metrology results are optimal, right? So that you have uniformity across the die, uniformity from die to die, and then obviously wafer to wafer. So the accuracy of placement of the wafer in that alignment process is critical, and then the subsystems within the lithography system will then do the registration and execute the exposure so that the pattern is printed with the right fidelity.
Is it that accuracy that makes this so difficult?
Yeah, it's the repeatability from layer to layer. If you think about defect mechanisms in the semiconductor space, obviously, particle deposition on a wafer is typically resulting in killer defects, depending on the size of the particles. But there's also a process-induced yield outcome based on critical dimension control and layer-to-layer registration. And it can be not just between one layer and another, it could be through 3 or more layers in the process, where you get a situation where you could have a 3-dimensional defect arise from the combination of error stacking, right? From a deviation in the CD, a deviation in the overlay, resulting in a misregistration of a contact or via in the process, such that you have an unreliable device, or maybe a device that would fail through initial test, functional test. So yeah, it is critical, absolutely. And it's not just a single pass metrology step that matters. It's the relationship between the layer to layer performance in the process.
So what comes next? I mean, as the lithographies get tighter and tighter, does that just make your job harder and harder?
Well, I think certainly the evolution of encoder technology in lithography has progressed with the demands of the technology node transitions.
Mm-hmm.
I think we go EUV, or as we see EUV implemented, maybe there's fewer lithography steps involved in certain types of structures that are printed,
Mm-hmm.
particularly critical layers. But I think there's other evolutionary process that's ongoing at the moment, which isn't necessarily related to front end, it's actually related to back end, which is the advanced packaging space. And in the advanced packaging space, we are seeing this trend of integrating memory and logic devices into the so-called chiplet system integration strategy for basically stacked hybrid memory stacks alongside logic devices, or high density memory with logic. And the strategy there is to improve the individual yield outcome of individual devices, but also have a way to integrate so that you have higher performance systems and drive greater efficiency in terms of the compute demand. In that case, though, you're bringing the, let's say, alignment and placement accuracy of devices into those subsystems closer to the front end requirements. So what's very interesting for us as a company that's already been very strongly positioned in the front end of line applications is that we can take the lessons that we've learned, the technology that we've developed, and apply that into the back end of line. So, as you're getting down to, 150 nanometer, let's say, placement accuracy in future, let's say, chiplet architectures, that's where the front end of line technology problems that I've solved before then become applicable in the back end of line. And I see that as an emerging need that will drive material choices, that will drive, let's say, chiplet integration system design architectures, and ultimately will drive the need for high precision and accuracy of motion control.
Very good. I find this extremely interesting, and I'm sure we could talk about this forever, but I'm afraid we're out of time.
Well, thank you very much, Rich, for your time, and I hope I've been helpful in explaining Heidenhain's position and some of the key drivers in the semiconductor industry that's challenging us today.
Absolutely. It's pretty complicated stuff, and if I could understand it, then you did a good job.
Thank you so much.
That was David Doyle, the President and Managing Director of Heidenhain, and I am Rich Nass with Open Systems Media.